Swayam Prabha. Digital India. Educated India.
Hello and welcome to another lecture on control systems. Over the past two lectures we have been discussing this Nyquist plot, this topic Nyquist criteria, and how apparently this is supposed to help us in inferring about the closed loop stability of a transfer function given the open loop plant cum controller transfer function, right. So we have come up with this criteria in the previous lecture where we saw that if you are able to sketch this particular Nyquist diagram based on this chosen contour in the clockwise sense on the Argand plane, then just by counting the number of encirclements, the counterclockwise encirclements of -1 plus j0 on the GC plane, where G is the plant transfer function, C is the controller transfer function. So originally what we started off with was this encirclements of origin in the 1 plus GC plane, and then we showed in the previous lecture that that is tantamount to counting the encirclements of -1 plus j0 in the GC plane. Yeah, so if that is as convenient as that, then why just unnecessarily add 1 to it and then complicate matters and plot it on the 1 plus GC plane. So we just plot it on the GC plane and look for encirclements, counterclockwise encirclements of the -1 plus j0 point, right, and that we equate to P minus Z, where P is of course the number of open loop poles of the system in the RHP, and Z is of course the unknown which is to be determined, that is the number of closed loop poles of the system in the RHP. Okay. So with that in mind, now let us get down to the business of trying to see for ourselves if we can actually plot some of these Nyquist diagrams for these systems, right. So one of the first such examples we are going to take is something that we are very familiar with from our studies of root locus. So let us consider this k by s plus a times s plus b times s plus c, right. Yeah. So yeah, that should be our open loop transfer function. If you want to combine the CS and the GS, so that is a loop transfer function, let us say. So let us say A, B, C are all positive real numbers, right. So we know what the root locus for this looks like, just a rough sketch like this. Yeah, you know that the root locus exists, let me draw with a different color. So the root locus exists between this and on this. So then of course we know that there will be asymptotes that go like this. So eventually this root locus goes like this. Yeah, and at a certain value of k, if this k is your variable, if this is variable, then at a certain value of k you will see that it will cross over to the right half plane. But okay, all in good time. We will actually do a detailed parallel study of these three tools, this root locus, Nyquist and Bode, and see the parallels between them, but that is later. Right now our job is to be able to come up with some similar rules that we had for root locus in this Nyquist case, yeah, to see how we can draw this Nyquist diagram, which we are claiming as a frequency domain tool. Alright, so to start off with, we first have this D. Well, you can immediately see here that this is not a defective case. I probably shouldn't call it a defective case, but in the sense that you see the open loop poles, none of them lie on this boundary, this imaginary axis, right. So we can safely and without much worry or concern take this to be our contour that we want to map. This is an infinite contour that we want to map. So this is our Argand plane like so, and we want to pass on our Fs, which is going to be this k upon s plus a times s plus b times s plus c, yeah. And instead of looking for encirclements about the origin, yeah, on the Fs plane, we look for encirclements about the -1. So this is our critical point, -1 plus j0, this is the real part of f, and this is the imaginary part of f, yeah. So how are we going to do this? So at some crucial points, let's just split this contour up into convenient segments. So let me just call this segment here A, this as B, okay, let me just mark it with an arrowhead to denote the sense, and this as C. So look at the segment A to B, and on this same plot itself, let me draw the 3 poles, because it will be really convenient for us to see how this changes. So now at this point you see omega is equal to 0. So what happens? F of 0, yeah, we see that it is nothing but k upon ABC, right? It is just a real part, purely real number. So let me just mark out this point here, maybe in this color, yeah. So this is just the point k upon ABC, right. So of course at omega is equal to 0, this is where this particular Nyquist plot will start from. Now what happens as this sort of omega is increased? How are we increasing this? So we are going from the segment A to B. So you see already I have this point A dashed. So this point A, it maps to this point A dashed. It is straightforward to see through this mapping, right. I have just plugged in s is equal to 0, which is what this is. A is basically the origin of the Argand plane. So the origin maps to this point k by ABC, right. Now we are going to map this segment of the contour A to B. Now what happens? Again, be mindful that we are not really concerned with the magnitude so much, right. It is the argument, it is the phase that really is of our concern. So of course there are several points. So you have a test point here, for instance. So let us say this is S1. What happens to this? This is some phi 1, this is phi 2, and this is phi 3. So at this point S1, what is the net phase of this transfer function? Yeah. So f of S1 is equal to 1 upon magnitude wise S1 plus let us say this is A, B, C like this. So S1 plus A, magnitude wise S1 plus B, and magnitude wise S1 plus C, yeah. But they will also have some phases, and their phases will get added. So this phase will be phi 1 plus phi 2 plus phi 3, right. But now if you want to rewrite this in the nice form, so then this is basically something like R with an angle minus phi 1 minus phi 2 minus phi 3, right, where R is obviously equal to 1 upon S1 plus A mod times S1 plus B mod times S1 plus C mod, yeah, that is R. But notice, what are these phi 1, phi 2, phi 3? As we are changing this angle here, these are all in the first quadrant. So these are all positive angles in the first quadrant. So therefore the negative of those are basically negative angles in the first quadrant, negative angles in the fourth quadrant, that is, right. If phi 1 is positive, then minus phi 1 is in the first quadrant, minus phi 1 is in the fourth quadrant. So minus phi 1 is in the fourth quadrant, minus phi 2 is in the fourth quadrant, minus phi 3 is in the fourth quadrant, alright. So they will sum up and they will lead to a rotation in this direction, in the clockwise direction here, right. As you keep going like this will somehow tend to move in this fashion, no. This is how this will move. Now of course if you are taking it very close to the origin, then all these 3 phi 1, phi 2, phi 3 are very small angles, but nonetheless they are small negative angles, yeah. So maybe if this S1 is, if S1 is close to A, then phi 1, phi 2, phi 3 are small. Yeah. So initially as you start your journey along this contour, part of this contour from A to B, yeah, so this is, let me rewrite that, this is A, yeah, so that A is probably not visible, hardly visible, yeah, so now it's probably better, yeah, so this is the A, yeah, so this is phi 1, this is phi 2, this is phi 3, right. So if you choose this S1, a test point very close to the origin here on this segment of the contour between A and B, you see phi 1, phi 2, phi 3 are small. If phi 1, phi 2, phi 3 are small, their sum is also not very large, I mean just on a qualitative sense, but they are of a negative value, right, these phases are negative. So what does that tell you? If phi 1, phi 2, phi 3 are positive, then minus phi 1, minus phi 2, minus phi 3 will be in the fourth quadrant, a point on, they will be denoting points on the fourth quadrant. Yeah. Now the sum is not too big magnitude wise, so the sum of phi 1, phi 2 and phi 3 will also remain in the fourth quadrant, and of course this is also obvious from the continuity of this plot, right. So if you choose this point, maybe a point here will be your FS1, yeah. So if you start your Nyquist plot here, you will go like this, okay. So you will eventually go like this, but where will you end? So where does this point B map to? That is the next question. I mean we can keep going like this, where does this point B terminate? One thing is obvious, at B omega is infinity, j omega is like j infinity, right. So at infinity obviously this Fs will vanish, it will go to 0, but remember it is a complex variable, so it can go to 0 along any of those directions, right. It is not just the real axis where you either approach 0 from the left or from the right. Here you can approach 0 from any direction. So along which direction will it approach 0? So one thing we know is that it will eventually end up at 0 here, yeah, but along which direction? That is now the critical question, right. So how do we evaluate that, or how do we get some idea about that? Well, again you consider this same contour here, maybe I will redraw it, otherwise it looks a little clumsy. So let us redraw this contour here, and you have these 3 points here, this is minus A, minus B, minus C, okay, did I miss the minus sign here? Probably, yeah. So this will be minus C, minus B, minus A, yeah, right. Now you see here, this is the point B. At point B, what is this angle? I mean of course the way I have drawn it, it looks like some angle less than 90, but you know at the end of the day this is infinitely long, right, this is infinite distance away. So this is like 90 degrees, this is also 90 degrees, even if you know your eyes are deceiving you here, this is also 90 degrees, yeah, as you keep going very very far away along this direction, this is 90 degrees. So what is the net contribution? So you see this is going to be some k times epsilon 1, sorry not epsilon 1, k times some r1, yeah, so this is let us say r1, the length of this segment is r2 and the length of this segment is r3. So r1 with an angle 90 degrees, r2 with an angle 90 degrees, r3 with an angle 90 degrees, and what about r1, r2, r3? r1, r2, r3, all three of them tend to infinity, because you are now at an infinite distance away from each of these points, right. So these lengths of these segments are also infinite, yeah, if you have to meet a point that is infinite distance away, then the length of the segment is going to be infinite as well. So this is going to be nothing but almost like you can think of this like some k times some epsilon cubed, yeah, with an angle minus 270 degrees, yeah, because 90, 90, 90 is 270 and it goes up in the numerator, so it is minus 270 degrees. Now where on earth is minus 270 degrees? Yeah, on the GC plane, so this is the real part of GC and this is the imaginary part of GC, which is my F now, yeah, like I have drawn here. So now my F is basically GC, yeah. So now where does minus 270 degree go? So minus 270, now this is why it is important. See, earlier when we were drawing this, we said that this plus or minus sign, yeah, this plus or minus sign is dependent on whether it is agreeing with the direction of rotation of the contour, that, but now you are evaluating a complex number. This is the usual convention. So what is a complex number with a phase of minus 270? Forget about the Nyquist thing. The Nyquist thing, that encirclement when we are counting, yeah, when we counted the encirclement and all, then we said that, well, when we are counting for this positive encirclement, yeah, it is basically counted in the counterclockwise direction, right. And then we said that, well, you can have a clockwise encirclement which is then counted as a negative number, yeah, and then we said that, well, that has got to do with the fact that, well, when we, let us say, let me go back a few slides here, maybe here or maybe a little before, right here, yeah. So here we said that, well, 0 gives you the same direction of encirclement, so it is a plus 360 degrees, yeah, that is the slide, yeah. So remember, do not confuse this. I really want to linger on this point a bit because I do not want you to confuse these two concepts. Here, now you might say that, well, here you said that plus 360 degree corresponded to a clockwise rotation, yeah, but that is because when we were counting for this principle of argument based approach, then we said look for the direction of rotation in the Argand plane. If it is clockwise, then an analogous rotation in the FS plane which is clockwise will count as a plus 360 degrees, alright. So this is the reason in some textbooks they actually take the contour in the Argand plane in the anti-clockwise direction, then it does not create this confusion. Unfortunately, with the convention that we have adopted, of course it has its benefits because later on we shall see that, but with this convention it might create some confusion in your mind, do not get confused, yeah. Here this plus 360 degrees, and I really want to again hit on this point, here this plus 360 degrees has got to do with whether the contour in the FS plane is in the same direction, is rotating in the same direction as the contour in the Argand plane, okay. So you choose a contour in the Argand plane, that is clockwise. So if the 0 is included inside that contour, then the rotation due to that 0 is also going to be a clockwise encirclement. So that sense it is positive, okay. If it agrees, if the two contours agree, then it is a positive rotation. If the two contours oppose each other, the contour in the Argand plane and the contour in the FS plane, if they are in opposite directions, which is what happens when you have a pole inside, then it is counted as a negative rotation. It has nothing to do with whether it is clockwise or counterclockwise in the absolute sense. So if you had chosen your contour in the Argand plane to be counterclockwise, unlike what we did here, then you will see that this Z1 will still be plus 360, yeah. Then the contour in the FS plane will also be in the counterclockwise direction for a 0 and in the clockwise direction for a pole, yeah. So it is always going to be like the 0's encirclement, yeah. If there is a 0 inside a contour in the Argand plane, then that point, that contour maps in the clockwise direction if it is in the clockwise in the original case. If it is counterclockwise in the original Argand plane, then that 0 results in a counterclockwise encirclement of the origin in the FS plane. The pole will always be of opposed nature, right. So in that sense this plus and minus should be read and understood, okay. So this plus and minus does not have anything to do with the absolute notion of counterclockwise as positive and clockwise as negative, okay. This is about comparison between the rotations in the Argand and in the FS plane, whereas what we are doing now is when we are evaluating this function here, then this angle has got nothing to do with the direction in which it is being rotated in the Argand plane, no, because this is like an absolute sketch, yeah. Irrespective of how I have landed up at this point B, whether I have come from A to B or I am going from B to some other point, at the point B, so this is a pointwise function, pointwise evaluation of the function. So it has got nothing to do with the direction in which you are traversing this. Yeah, the value, if you pass on a value of s at infinity, at j infinity, yeah. So basically you are saying that s tends to j infinity. At that point, how you have arrived at this point B is immaterial, yeah, this contour is inconsequential. All that you now need to do is to pass on this argument j infinity, or if you, with an abuse of notation of course, you pass on this in the transfer function and evaluate it, and then you get minus 270. So what does minus 270 tell us? Minus 270 tells us, as we understand rotations, counterclockwise are positive and clockwise are negative. This is in the conventional sense, forget about this Nyquist that you have learned, just think of complex numbers, yeah, counterclockwise is taken to be positive rotation, clockwise is taken to be negative rotation. So minus 270 means a minus, so minus 270 means you go 270 degrees in the clockwise direction. So this is the way in which you will be approaching the origin, okay. So it will be a point somewhere over here, right. So now if I want to complete this sketch here, I will come up with a point somewhere over here. So this point B will map to this point B dashed over here. I'll draw a fair sketch of this at the end. So this is just a rough. But now comes the interesting bit, and you might think that I am making too fine a point on it, but it is probably still better to understand this at a conceptual level. So what is it? Now we have to map this entire D, this big contour, right, all at infinity, this entire path that is traversed here, yeah, now we have to map this fellow here on the Fs plane. You might wonder how are you going to do this, but remember all of this, because of the fact that this function Fs is strictly proper, this entire region will only be within the vicinity of the origin. And notice another thing, so why I said this is actually too fine a point which will not in general matter much is because of this, okay. See, once we are plotting it in the GC plane, we are not concerned with the encirclement of the origin, we are concerned with the encirclement of minus 1 plus j0. So whatever small dents and nice cute little things that are happening in the vicinity of the origin, they will in all likelihood not even matter to this critical point for us, right, yeah. So in that sense, even though I am saying that okay, we are very particular to in our desire to sketch this, but it will turn out that this is not really such a big deal. I mean, it will not matter much insofar as our stability deductions are concerned. Nonetheless, it makes sense to try and understand how this behaves. So now for that, let us pass on this argument and see where the point C maps to. So this is the point B where it maps to, yeah. So the point B maps to this. This is basically my B dashed. So this is B dashed, this is A dashed. What about the point C? Which is the point C? This is the point C. This is the point A, this is the point C. So B to C I am traversing in this fashion. So what happens? What is the pointwise value at point C? Yeah, if I just measure that, so that is minus j infinity. S tends to minus j infinity. So what does that mean? I am going to just pass on, you see if I try to map this again in the same fashion, I am going to again write R1. What is this point? This is with an angle minus 90, right? This is minus 90 degrees, then R2 with an angle minus 90 degrees, and R3 with an angle minus 90 degrees as well. So this is minus 270 when it goes up to the numerator. So this is basically going to be like epsilon cubed with an angle 270 degrees, yeah. So on the face of it, this point C dashed is going to be 270 degrees. What is, why 270 degree with a 0 is point mapped here? Because now it is a plus 270 degrees, so it is a clockwise, it is a counterclockwise rotation, right. So it goes like this is 90 degrees, then this is 180 degrees, then this is 270 degrees, yeah. So it comes somewhere like this. But you might ask, how does it go from B to C? Yeah, so this is, I understand that this is C dashed. What about the traversal along this, all this journey, this 180 degree traversal on the Argand plane? Yeah, this is a 180 degree traversal, no? Here S is equal to R with an angle 90 degree, here S is R with an angle minus 90, where R tends to infinity. That is what j infinity and minus j infinity are, right. J infinity is basically, you can think of it as r with an angle 90 degrees, and minus j infinity is basically r with an angle minus 90 degrees, right. And this r1 and r are almost the same, because obviously these points ABC, looking at from the vantage point of this point that is at infinity, these points almost look like they are at the origin itself, right. This is some similar argument we have seen when we are talking about the proof of Routh-Hurwitz criteria, if you recall, right. We use the same sort of thing when we are doing root locus as well, right, when we talked about the asymptotes, evaluation of the angle criteria, and to find out where, along which direction the asymptotes will head. It is the same sort of analysis that we did there. So it is not something we are not familiar with. The thing to remember here is, of course, that at C, this is the point C prime, right, but we are still to figure out how it gets from B dash to C dash. So in order to understand that, we understand the total phase change from B dash to C dash. So notice at B dash, it is at a value of epsilon minus 270 degrees, and at C dash, it gets to epsilon with an angle 270 degrees, right. So the final minus initial, so this is the final and this is the initial. So if I take the final minus the initial, then what is the net rotation that is happening? It is 270 minus 270, yeah. So this is 540 degrees. What is 540 degrees? 540 degrees is like 3 180 degrees, or rather one complete 360 degrees, yeah, in the positive sense. So one complete 360 degrees in the positive sense, yeah, and then another 180 degree. What does that entail in terms of this diagram? So you see, if I now try to draw this part in fair, it will come something like this here, which I have already drawn in the previous diagram, but yeah, I am trying to draw it in a better fashion here. So this is B. So this is being traversed in this sense, right. So this is clockwise, but now this entire segment, which is clockwise in this Argand plane, this will lead to a net counterclockwise phase transition of 540 degrees, because this is plus 540, remember. So this is the final minus the initial is plus 540 here, yeah. So if it is plus 540 here, then I wonder what this is going to look like. Well, you need not worry too much. Let me draw the critical point here, since I am drawing it here. So what this will then look like is, it will come once like this, yeah. So this is one complete rotation, right, and it will just, let me see, just hang on. So it has ended up here at this point, and then it will basically try to rotate once around this this entire circle here, yeah. This is one 360 degrees, and then like this, okay, yeah. So it just goes like this. So note that looking from the origin, this looks like one complete rotation and then like this. So let me enlarge that a bit for you to be able to see, maybe in the next slide. So notice where was B dashed and where was C dashed. So B dashed is on top, C dashed is below. So you have ended up at B dashed over here, and this is your C dash. So I am just enlarging that. So now you want a 360 degree rotation of this point. So how does it happen? So it goes like this and like this. So I urge you to check that this, in going from here to here, it is already a 360 degree, then another 180 degree is where it goes like this, yeah. That is what it is, okay. So this entire infinite radius, about which I happen to have been so worried initially, yeah, it just turns out like a small dent around this, very minor dent around this origin, which I could hardly care about, yeah. So in practice, if you do not draw an infinite radius and you draw a very large radius, you will get a small dent around this point. Yeah, for the purpose of a Nyquist sketch, we do not really bother with this because our critical point is -1 plus j0. So these small things happening around the origin are hardly of any consequence to us. So this, so then I kind of now can figure this out how this is happening, and notice that now if you want to really take a shortcut, all that is left is evaluating how this Nyquist plot evolves as we go from C to A. But I am putting it to you that you do not really need to evaluate that separately. Yeah, why so? Because you see, because of the symmetry, the very symmetrical nature of this, yeah, whatever happens at this gj omega for positive omega, and then you want to sketch g of minus j omega for positive omega, yeah, it is going to be a reflection, because after all, you see, if you take a complex number, so okay, let me just be a little precise about this. If you take a complex number which is a plus ib, and you take its conjugate, or a plus jb rather, you take its conjugate, it's a minus jb, right. So you know that if you have a complex number on the Argand plane here, this is z, then in order to sketch z conjugate, you just need to look at its reflection about the real axis, right. And what is the difference between the number and its conjugate? It's only the sign of the imaginary part. So the same thing happens here, right. You see, whatever is responsible for imaginary part, yeah, is this j. So in j omega, if you just replace this j with a minus j, you are basically getting the conjugate, yeah. So every point here that you have sketched from a dash to b dash corresponding to this segment from a to b has a conjugate from c to a, yeah. So therefore I will not go through the trouble of re-sketching this again and evaluating this c to a. You can of course try and convince yourself, because you are already at c dashed, so you can try and convince yourself, and you will know that this a dashed, and this a dashed is where you will have to end up. You start from c dashed and you end up at a dashed, but how you are going to go, that detail is now really a trivial point, yeah, because now I can just take this this point here, and I am just going to complete this like this. So even though my sketch does not look symmetric, trust me that this is okay. Maybe this is too bad, so let me try to make it appear a little more decent than that. Yeah, okay. So this is a dashed. So this is just the sketch, no. So this is c dashed, and the c dash to a dashed is basically the map of the c to a. That's it. I have sketched the Nyquist plot. So now you see, this is how piece by piece we take parts of the contour. There are mainly these three important parts for a general transfer function: the positive imaginary part, the negative imaginary axis, yeah, and then this d, this that goes around this infinite values, right, across from pi some pi by 2 to minus pi by 2, yeah, if you go from it in the clockwise sense, right. So this is how you sketch this. So we've actually sketched this general, just like we had this root locus sketch for this particular type of system. Now we see that drawing the Nyquist plot, of course if you are very finicky about getting the exact magnitude and all, then you should prepare a table and take some critical points and then draw this, right. But you know, qualitatively we are pretty reasonably happy. The one thing that is important, okay, among all of this, the one point that is really important as you drew this part from A to B, notice, is this particular point, yeah, because notice that if this particular point, so let me draw the arrowheads here, so it's going to be clear. So notice that if this point here were to include or were to enclose or encircle this minus 1 plus j, then excuse me, then you might have had what should I say, a Nyquist diagram, yeah, this yeah, so we have this here, so you might have had a Nyquist diagram where should I draw it, maybe on the same curve, yeah. So you might have had a Nyquist diagram that was like this A double dashed, yeah, and then you might have had this included here, yeah, like this, or should I have used a different color, maybe. So if you increase the K sufficiently, you might have ended up with a Nyquist diagram that looked like this, yeah, and then of course this small dent, it would hardly be distinguishable from this, yeah, it would look like this, and then you would have this thing like this, yeah. So this would then have been the Nyquist diagram, okay, if this crossing this. So therefore this point is very crucial. Later on we will see, we will relate this, once we have familiarized ourselves with the sketching techniques, we will relate this to things like phase margin and gain margin, with which we are already familiar. But for now, among all the points, this A, B, C and all of these things, yeah, it will turn out that this point where this imaginary part is 0, of course at the starting point itself where S is equal to 0, the imaginary part is 0, but apart from that, where the imaginary part is 0 and the real part is negative, that frequency is going to be very crucial, okay. Turns out that this frequency will be exactly that phase crossover frequency. So we will talk about that when we discuss more about the stability notions in the view of this Nyquist criteria. We will do that shortly, maybe in the next lecture or so, but you know, this particular frequency is also a crucial one, because this will tell you that at that particular frequency, whether it is cutting the negative real axis at a point beyond -1 plus j0 or to the right of -1 plus j0, because that will tell us whether this point is encircled or not. So for example, in this blue case here, this blue line here, if you draw a test radius like so, you will see that there are 2 clockwise encirclements, yeah. So if there are 2 clockwise encirclements, what does that tell you? N is going to be equal to -2. So -2 is going to be equal to what is P? You see, P is basically the number of open loop poles in the RHP, and we have already said that A, B, C are all positive numbers, yeah. So if A, B, C are positive numbers, these are open loop poles, so minus A, minus B, minus C are in the LHP, yeah. So therefore the number of open loop poles on the RHP is 0. So then this is going to be equal to 0 minus Z, which basically tells me then that Z is equal to 2. But what is Z? Z is basically the number of closed loop poles. So this also tells you something interesting, exactly what the root locus told you, right? The root locus told you that you cannot have a situation, look at this root locus. So if there is a critical value of K, so at a value of K less than that critical value, you have all your closed loop poles on the left half plane. But as soon as you cross over from the critical value, you see you will have exactly 2 poles. You cannot have just one pole migrate to the left, okay, or to the right. You will have 2 poles migrating simultaneously to the right. Now here the Nyquist criteria is telling you exactly the same thing, yeah. It's going to tell you that as soon as you cross over, yeah, as soon as you let's say what you are doing is you are increasing this value of K, yeah. If you are increasing this value of K, this gets enlarged, because you see that after all this A, the value at point A is dependent on K, no. So if you make K large, you will be cutting at, this at A double prime, yeah, which is basically larger in magnitude than A prime on the FS plane, on the GC plane, right. So therefore you see that this Nyquist plot is going to blow up like a balloon, it is going to get inflated in every sense of the term, because now this K is larger. So at every value, every corresponding frequency, it is a conformal map, it preserves the shape of this, yeah, but the size gets blown up, because all you are doing is after all just increasing it by a constant scaling factor K. So at every point whatever was this, yeah, it just gets blown up, yeah. So if it gets blown up, then you see that eventually at some point, this so called, what I have said, the phase crossover or the negative real axis cutting, this goes and crosses over and includes this critical point, and when it includes the critical point, the number of encirclements changes suddenly from 0 to -2, If it changes from 0 to minus 2, then z changes suddenly, because p is going to always remain 0. P is a parameter that depends on the open loop poles, which is going to be 0 in the RHP, right, because ABC are positive. So therefore, there is a sudden jump from 0 to 2, but it cannot be just 0 to 1. Yeah, so the same thing that the root locus told you, the Nyquist is also telling you, right. So Nyquist is exactly containing equal amount of information insofar as these sort of inferences are concerned. Okay, so this is just, you might say, okay, this is a toy example, it's a simple kind of a Nyquist plot. For root locus we drew so many complicated kind of root loci, yeah, we had this complementary root locus and stuff. So I wonder, if Nyquist is going to be able to handle those things, yeah, and if so, then maybe it will come at some cost, it will be probably a little more complicated. How are we going to handle those? So well, we have already seen a hint of what could complicate matters insofar as Nyquist is concerned. The moment you have some of these open loop poles on the imaginary axis, it turns out that Nyquist can give you a little bit of a pain. So how do we try and overcome this sort of difficulty, or is it really as big a difficulty as it appears to be? So what I will do is I will take repeated poles at the origin. I could have taken a single pole also, but I will take repeated poles at the origin. You can actually try as an exercise considering purely imaginary poles and seeing how they would behave. Okay, it is an interesting exercise, but it will follow essentially the same principle. Maybe if I have time I will just talk briefly about it, I will not take a numerical example. So let me take another example here. The second example I am going to consider is, say, s plus b upon s squared. Okay. So let us say this is the transfer function for whom I have been asked to draw the Nyquist. So immediately you see that there is repeated poles, so you cannot, as a matter of fact, take the pure D contour in the Argand plane. You will have to exclude that point, that origin. So how do we do this? So I'll choose, as I said, I'll choose to exclude it instead of including it. There's also this way of including it, right, but I'm not going to include it, I'm going to exclude it. So I'm going to modify this D with a bit of a dent here. Now what that does is it introduces an additional point. Earlier I had this A, recall, here I had just this point A here, right. So now I'm going to just have two more points, yeah, so I'm going to have this A1, yeah, this is B, this is C, and this is A2. Because there is this dent here, so I am going to just include that A1 and A2, they will be separated, right. So what is the number of poles here? There are two poles here. So of course there is a double pole here, and then there is a 0 over here, right. So let us just try and understand what the root locus is going to be, yeah. So we already know that in this case the root locus behaves something like, it goes over like this, and then one branch goes to the left, so that is just going to be one asymptote, because the relative degree is, yeah, so this is the root locus, this we already understand very well, this is minus b, so of course b is, we are taking b to be positive, so this is minus b, right. Now instead of having 3 segments as before where I had AB, BC and CA, I will now have actually 4 segments, because I have to also account for this small dent here, that's the only part that changes. So how are we going to address this? So consider AB mapped to A dashed B dashed, or rather A1B mapped to A1 dashed B dashed in the GC plane. Okay. So how is this A1 going to map at the GC plane, right? Again, so GC is equal to K times S plus B upon S squared, and A1 is a point very small, very close to, like, So what is the total phase contribution here? You see, this is a point very close to the origin, like infinitesimal distance. So from looking at it from the vantage point of minus b, there is hardly any angle contribution. Yeah, so this is 0. What about the angle contribution from the double pole at the origin? Well, it is going to be like, so this is going to be KB, and there is going to be epsilon with an angle 90 degrees and another epsilon, because there is two poles here, so with an angle 90 degrees. So this is going to be like some large number r, so limit epsilon tending to 0, this is going to be like limit r tending to infinity, r with an angle what? Minus 180 degrees, yeah. So what is this point minus 180 degrees? Minus 180 degrees means you have to go about a clockwise rotation starting from this reference, which is the positive real axis, of course not this axis, it is in the Fs plane, yeah. So let me take this real part of GC, this is the imaginary part of GC, this is my reference point. So I have to go about minus 180 degrees, which is a clockwise rotation. So I go about this, so this is my minus 180 somewhere here, and the magnitude is infinite, yeah. So this is my point A1 prime, alright, this is my point A1 prime, sorry that was a bad sketch. So this is my point A1 prime somewhere over here, right. Of course this is almost like 0, I mean I have just made this small distance here, at infinity this distance will hardly matter, so this is like minus 180 degrees, okay. But now I have to understand where it goes as I head to B. Notice that as you go from along this line, these two, this double pole here, that keeps on contributing minus 180. The only thing that changes is the contribution due to this minus B, yeah. So you, for example, you take sample points here, 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 insofar as the contribution of this double pole is concerned, yeah, as I said in Nyquist we do not really care about the magnitude, so it is just the phase that I shall be talking about here. So as you go from this S1, S2, S3, the phasors joining this double pole to this S1, S2, S3 will always be vertical lines. So this is just going to be like 90 degrees, yeah. So it is always going to contribute this minus 180 degrees throughout. Only thing, the magnitude will get smaller because the distance now increases. So it is no longer infinitesimally close to the origin as in A1 was, right. So now the only thing that happens is, now notice that this angle contribution of the 0, this is phi 1, this is phi 2, and this is phi 3. So you see, as you keep increasing, going along from A1 to B, the contribution due to the 0, this left half plane 0, actually increases. What that will end up making is, you have this minus 180 plus some positive contribution, yeah. So the contribution is basically at on segment A1, okay, this is A1, so A1 to B of contour, yeah, phase is phi minus 180 degrees. So this phi is a function of course this omega, and phi of omega is positive. What does that mean? You see, you went about clockwise, that is why it was a minus 180 degree, and now it is going to add some minus, it is going to add some positive angle, so that is a counterclockwise rotation, right. So as I said, I will not really be bothered about what the exact shape of this curve is, but the only thing that I am particularly concerned about is that eventually, yeah, this, if I go from this point, so this is, let us say S1 and this is S2, I am not really worried about what the magnitude is, but the one thing that remains constant is that you see the phase contribution, yeah, this phi omega's contribution increases, yeah, eventually until as it goes to this point B, the maximum contribution that B, this phasor can give is 90 degrees. So eventually it will have minus 180 plus 90, which is equal to minus 90 degrees, right. So what is minus 90 degrees? Minus 90 degrees is along this direction, no. So eventually it will end up at a point somewhere over here, right. So here I have mapped this point B, okay. So again I am not taking any responsibility for the shape of this, yeah. We will eventually see that maybe in most cases they will be well behaved and you will not have too many nasty sort of bends and meanders like this, but you know I am not making any guarantees about that, okay. All that I am saying is that as you move along this direction from every point to every other successive point, if you go along this direction, if you keep mapping this segment A1 to B, yeah, the phase contribution of the 0 gets more and more positive until it gets to plus 90 degrees at the point B, which is when this contributes plus 90 degrees minus 180, so it becomes a minus 90 degrees, the net contribution, right. So therefore it ends up at a point here. This is going to be your map of B, which is B dashed, right. Now of course then it's the next segment, like what about this whole large thing here, this B to C, yeah. So what about it? Let us again approach it in the same fashion as we did in the previous, and now you will begin to see the pattern here, yeah. So what did we say about this earlier case? We will exactly follow this same approach here. So see, at B what is the net contribution? It is minus 90. At C what is the net contribution? Again these two fellows will contribute. Let's consider this. At C net phase is, well, you see it will be something like angle. So here what about these two double poles, this double poles? At C they will all have minus 90, both have minus 90, so minus 90 is minus 180, but because these are poles they appear in the denominator, so they will go up and will become plus 180. But what about the contribution of this fellow, this 0, yeah, this becomes minus 90, so it is 180 minus 90, that is net result is plus 90, yeah. So of course we could have also deduced that this from the symmetry argument that we said, right, the conjugate. So this is going to be the point C dash, but now how are you going to traverse this? So this is 90 degrees. So again final minus initial is going to be 90 minus 90. So this is at C dashed and this is at B dashed. So your journey across this entire large contour is basically encapsulated within this B dash to C dashed, yeah. So what is this final point C dash minus the initial point? This is going to be 180 degrees. 180 degrees means plus 180 degrees, which means that it is counterclockwise, yeah. So what is a counterclockwise rotation of this point here? You see, if I want to encircle or go around the origin in a counterclockwise fashion here, then I better sketch it in this fashion, yeah, that is it, and I am claiming that I am done. Why? Because now I do not need to bother about, of course there is a big story still remaining, but as for the other part, from the symmetry argument you see, this segment from C to A2 I really do not need to worry, I will just draw a replica of this, yeah. So the C to A2, if you excuse my lack of ability to draw nice sketches, yeah, then this is my A2 prime. But the big story now remains. You see, in the earlier case, because we did not have to bypass this or any dent around this, right, this is where our story ended, yeah. Insofar as this sketch of this particular transfer function was concerned, we did not have any of those nasty things here, alright. But now the same cannot be said of this, yeah, because this A1 and A2 they do not coalesce into a single point A, yeah, there is a small encirclement that is going around. So I wonder what the effect of that encirclement is going to be. So this is like somewhat in some sense a dual. So this large contour, yeah, this large contour on the argand plane showed up as just a small dent around the origin, okay. I have drawn it very big here, but you believe me, this is very small, right. And now we will see, funnily enough, that this small dent in the Nyquist contour here in the Argand plane will actually result in an infinite contour in the GC plane, yeah. So how are we going to deduce what the direction of that rotation is going to be? Once again, our same old tool. Let's look at this. It's all just about complex numbers and figuring out how things happen. So see what's happening here. Between A2 and A1 is the segment that's remaining, right? So how do we join this A2 and A1? These 2 points, yeah? How do we go about this? There's got to be some encirclement. So what is constant between A2 and A1 is that the magnitude, yeah, of this j omega is very small. And if you also think about it a while, you will see that from the perspective of this point minus b, the 0, there is hardly any phase contribution, yeah, it is negligible, it is a small dent, after all it is an infinitesimal dent. So from the point of view of this minus b, there is no change whatsoever. But for these 2 double poles which I had to bypass through this sort of a cross cut or this dent, for them it is a big deal, because for them, see at A2 they had contributed minus 180 degrees, so in the transfer function they appeared as plus 180 degrees, but at A1 they are now contributing minus 180 degrees, yeah. So what is the, again we are going to apply this final minus initial. So my final is here, if I go along this direction, so I am going from A2 to A1, so my final is basically A2 prime, A1 prime, final is A1 prime minus initial which is A2 prime. So what is this? So you look at the final here, the final A1 prime which is here, right. So at A1 prime I know what the value is, I have already evaluated this, this is actually minus 180 degrees, no, this is minus 180 degrees. And what about the initial, that is this A2, at A2 also I evaluated it and I found that this is actually going to be, where did I evaluate it, maybe in the previous slide, maybe here, where did I evaluate A1, A2, let me check. Okay, never mind, I think I actually evaluated this, yeah, this is where it is, no. So this is basically this infinite thing, so this is minus 180 degrees, yeah. So A1 prime, so this is minus 180 degrees, right, okay. So A1 prime is the final destination where it is minus 180 degrees and A2 prime is where it is plus 180 degrees. So this is just 180 degrees, so this is minus 360 degrees. So that means I have to go around one complete clockwise rotation while going from A2 to A2 prime to A1 prime, which basically then entails, let me put the arrowheads here, which basically then entails that I have to go around, okay, that does not fit in this slide unfortunately. So this, yeah, so this is this infinite sort of contour that is being mapped, and maybe the critical point is somewhere over here, yeah. So you see once again very interestingly, and we will end with this note, interestingly you draw any test radius, yeah, you draw any test radius from here, yeah. So what is the net number of encirclements? You see once you have encountered this in the counterclockwise sense, once you have encountered it in the clockwise sense, so n is going to be 0, yeah. And what is going to be z then, because p is 0, so z is also equal to 0. So these we know now, so this we calculate. Not just that, it turns out that here no matter what you do to that value of k, for no value of k will you ever be able to encircle this critical point. But isn't that the same thing that the root locus also told us, I wonder. You see, the root locus also told us that if you increase values of k, yeah, the root locus completely remains within the left half of the S-plane all the time, it never goes to the right half, right. And the Nyquist is also telling us that no matter what you do to k, yeah, here also you see that you are never going to encircle this, the thing might get bigger and bigger or blown up, yeah, the shape might change, but once you have drawn this test radius, you will see that you will be cutting across the contour twice, once in the counterclockwise direction, once in the clockwise direction, hence the net number of counterclockwise encirclements is 0, because every clockwise encirclement counts as -1 counterclockwise encirclement, yeah, so it is 0, so therefore P is already given to be 0, yeah, because we have allowed this, remember we have excluded this point, so that is why P was 0, okay, we have excluded the double pole at the origin, we have drawn our contour to bypass this, so that is why P is 0, yeah. So if P is 0, N is 0, so P is 0 we already know, N 0 we figured from this qualitative sketch, and we compute Z is equal to 0, yeah, and that is it, and we deduce that this system is always going to be closed loop stable no matter what you do to the value of gain k, which is exactly what our this Routh array, if you apply, or if you apply this root locus, would also tell you, okay. So next lecture we will take up another interesting example, and we will show you another facet of this hopefully, yeah, and then maybe briefly I will talk about other purely imaginary roots and how things might be a little different, but really you should be now able to figure out on your own how to deal with these poles on the open loop poles on the imaginary axis. Thank you.